Okay, so in this video, we're going to be looking at integration via substitution. And you use substitution when you need to integrate composite functions, right? So that's when you know you need to use substitutions when you are asked to integrate a function that is composite. And we're going to go over various examples of what that looks like and patterns, because not all composite functions can be integrated using this method. You have to look for a specific pattern in those functions. All right. With this substitution method, I call it u-substitution. It's similar to the chain rule, which again, for differentiation, that's when you have composite functions. So let's look at this rule for the anti-differentiation or integration of a composite function. So let's look at this definition and kind of talk about what it's saying. So first of all, we're very familiar with this. This is the integral of a function f. Now the g of x that's what makes it composite. So you have the g of x inside of f of x, and then you notice it's being multiplied by the derivative of that function inside. That's where the g prime of x comes from. So you have to be careful. This function inside is always the function you're going to use as your u. Okay, this is always going to be your u, and it'll make sense when we do some examples, but always remember, when you're using your substitution, the function inside is always going to be your u. All right, and then this function outside, in order for this to work, and here's the pattern recognition, in order for this to work, it has to be the derivative or something similar to the derivative where things can, simplify or cancel out of the function inside. All right, so I think the easiest way is to kind of look at an example. Let's look at this example here. So you notice, first of all, you have an outside-inside function. The inside function is your x squared plus 1, and then your outside is 2x. All right, so think about your inside function being your u. So your x squared plus 1 is your inside function. Okay, now we're going to rewrite it. Instead of x squared plus 1 squared, it's going to be the integral of u squared times 2x times dx. Problem is, you have u and x, you have two variables, and we can't integrate when we have two different variables, so we have to get it all in terms of u. Now, over here, u prime, okay, so that's du. I'll write it as du to make it a little more sense. Du over dx, because it's the derivative of the function u with respect to x. That's 2x. Okay. Now, in order to do these substitutions, let's solve for just dx by itself. Just dx. And when we do that, you would have multiply over the dx. So be du is equal to 2x dx. And we can even stop there on this particular one. This doesn't happen all the time, but look, right there, 2x dx, 2x dx. We can make a direct substitution. So it would be u squared times, instead of writing 2x dx, it's just du in this case. Just happened to work out that way. If you don't recognize that, let's look at what happens if you don't recognize that. You keep going, solving for dx. Dx is equal to du over 2x. So we're going to make the net substitution. Okay. Instead of writing dx, we're going to substitute in u squared times du. Oops, I forgot the 2x there. 2x times, and I'm substituting in for dx. That's du over 2x. And you can see what happens here. The 2x's will cancel, and you're left with the integral of u squared du. Now we have something that we can integrate. Just like if this were x squared, you add 1 to the exponent and then divide by that new exponent. So this is u to the third over 3 and then you would have the plus c, of course. And now this is where you substitute back in. And we know that u is equal to x squared plus 1, so we're going to plug that in right there. So it'll be x squared plus 1 to the third over 3 plus c. That is our final answer. So we started with something that we couldn't integrate. We changed the variables by using substitution in there, and then we were able to then integrate it with those new variables, which is u, and then integrate it and then resubstitute in those old functions or old variables. So here's one. Try this one on your own. Remember, the u has to be the part of the composite function that is inside. So figure out which is inside in this case, and set that for u, and then go from there. So if we kind of walk through this step by step, first of all, I made the u substitution for 5x because that's your inside function. And then the derivative of 5x is just 5. That's this right here. And then I noticed, hey, 5 is equivalent to du over dx. So I just made that substitution right here. I just put it over here and I noticed the dx is canceled. And so you're just left with the integral of cosine, which is sine. So you get sine of u plus c, and then plugging back in for u, 5x, you get sine of 5x plus c. All right, let's take a look at another one. And I want you to do this 2 different ways. See if you can figure out how to do this 2 different ways. Number 1, using u substitution. And then number 2, without using u substitution. So see, try both ways, with u substitution and without, and then come back to the video to see how you did. You should pause it and work on it. Using u substitution, you should be able to recognize that, hey, x squared plus 1, that's the inside part, so that needs to be what I substitute in, because when you find the derivative of this, it's just 2x, which will end up canceling with that x, as we're going to see. Right, so we find the derivative, du over dx is equal to 2x, but we need to get dx by itself. So we go ahead and bring the dx over, divide by the 2x, so dx is equal to 2 du over 2x. And we're going to substitute that directly in there, right there. And you can see, nice and neat, the x's will cancel, and that's what was the point. We want the variable to cancel, and you're left with just 1/2 times u squared du, which we can integrate u squared du, just like x squared dx, add 1 to the exponent, divide by 3, and then you would have that 1/2 out there. Then I went ahead and multiplied 2 and 3, that's where the 6 came from, and then substituted back in the x squared plus 1 for the u. And that was our answer. Now, without using u substitution, if you need some help, you would end up multiplying this thing out. So if you haven't tried it, go ahead and do that. Multiply it out and then try integrating. Okay, so if you don't use u substitution, you end up multiplying everything out. Should look something like this. And I assume when you multiply the x squared plus 1 to the third, multiply that by 1/6, you'll end up with the x to the 6 over 6 plus 2x to the 4th over 4 plus x to, x squared over 2. Okay, so you can see u substitution was probably a little bit easier, a little bit faster, so that's why it's important that we learn it, because sometimes you won't be able to multiply them out quite like this. Let's take a look at another example. In this case, you have to use u substitution, but it's a little bit different because really you just need to change the variables. So use u substitution, kind of work through this and see what happens. Try this on your own and then come back. So we start off by using the inside function, the 2x minus 1, that is our u. Then we find the derivative. And when we find the derivative, you end up with du over dx is equal to 2. And again, we need to solve for dx because we're going to take the du over 2 and substitute it directly in for the dx, like what I did right there. And the 2 is on the denominator, so that can actually, when you divide by 2, that's the same as multiplying by 1/2. So I just brought that out into the front of the integral, since that's a constant. Then you would have the integral of just u to the 1/2. So you would end up adding 1, which is equivalent to 2 over 2. That's where the 3 over 2 comes from. Divide by 3 over 2, which is the same as multiplying by 2/3. And when you do that, that's where that 1, that's pretty 3. That's where that 1/3 came up out front there. Then you resubstitute in the do 2x minus 1 back in there, and you get 1/3 times the quantity of 2x minus 1 to the 3/2 power plus c for that one. So as you can see, we were not able to integrate first, but then when we did the u-substitution, all we did was change the variables. That's it, right? Math is all about using the properties to manipulate the numbers so that you can get them to do what you want. Having full control over them, the better you understand and know the properties, the better you can control the values and the numbers and get them to do what you want them to do. So here's another one, very similar. Let's see what you can do with this one. So try this one on your own, pause the video, and come back to see how you did. So you notice on this one, it's kind of tricky because when you replace the variable, you still have this pesky x right here. It didn't cancel out the x, right? So then we have to get super creative. And what I mean by that is, let's come back here and solve for x there and substitute that in. So if you weren't able to get past this point, pause the video, try that, solving for x, substituting that in for x, and see if you can get everything in terms of u and be able to integrate. So try that, pause the video, try it, and then come back. Like I had mentioned, you had to get a little bit creative on this one, where down here you had to get x by itself and then substitute that in. So in place of x, you put u plus 1 over 2. And then from there, it's a matter of simplifying because you can end up pulling the 2 out, and that's where the 1/4 came from. And then you end up just multiplying this into the parentheses of u plus 1. That's where the u to the 3/2 plus u to the 1/2 came from. And again, now we have all variables of u. Now we can integrate, and that's where the u to the 5/2 times 2/5 plus u to the 3/2 times 2/3, and then you distribute this 4 in, and you get 1/10 u to the 5/2 plus 1/6 u to the 3/2 plus c on that one. Involving a little bit of creativity for this one. Oh, and then the last thing is the substitution of u back in. My bad. So it would be actually 1/10 2x times the quantity of 2x minus 1 to the 5/2 plus 1/6 times the quantity of 2x minus 1 to the 3/2 plus c. Run another room. Okay, so that would actually be your final answer on that one. All right, so here's another one. I know there's lots of examples, but try this one on your own, see how you did, and come back to the video. So taking a look at this one, you start off by having u be in the sign of 3x, because that is the inside part. When you take sine squared of 3x, you can rewrite it as sine of 3x quantity squared. And so that is the inside portion of your composite, so that's why that is our u. And then when you find the derivative, you get 3 cosine of 3x by using the product rule, or the outside-inside chain rule. And then dx represents du over 3 cosine of 3x. And when we substitute that in for dx right here, those cosine of 3x's cancel, but you still have that 1/3. I pull that out front. That is my constant. Then I have the integral of u squared du. We can easily do by adding 1 and dividing by that new exponent, and that's where this piece comes from. But remember, we still have to multiply by the 1/3. Then resubstituting in the sine of 3x, that is our original u function. We resubstitute that back in, and we can either keep it here, or you can rewrite it as, since it's sine of 3x quantity to the third, you can rewrite it as sine third 3x. So it looks like this. Just they're the same thing, it doesn't really matter. All right, that's it for this video. We'll do some more examples and go over some guidelines for the next video, or in the next video.